Now that we have completed the requirements and relevance of mass and balance, regulations, terminology, weighing and determining the basic centre of gravity, we are in a position to move on to the more practical aspects. We will be solving mass and balance problems requiring us to find the position of an aeroplane centre of gravity. We will be using the information in CAP 696, single engine piston, as the basis for our calculations. Using the data of the single engine piston in CAP 696, we're going to complete a loading manifest shown on section 2, page 3, figure 2.4, and then plot the centre of gravity in the envelope shown on section 2, page 4, figure 2.5, checking that the mass and centre of gravity are within the limits shown on section 2, page 1 of the CAP. For this exercise, we will use some fictitious data to input into the loading manifest. Using figure 2.4 in the CAP, under the column heading Mass, enter the values against the appropriate item, and total the mass column item 1 to 7 to obtain the zero fuel mass, which we can see here is 3,295 pounds. Enter the arm for basic empty mass, 77.7 inches, which we get from the aeroplane description and data on section 2, page 1 of the CAP. Calculate the moment in rows 1, 2, 3 and 6 by multiplying each mass by its arm and dividing each one by the constant 100, and enter the result in the moment divided by 100 column. We can now total the moment column, giving the zero fuel mass moment. Before we enter the fuel loading, we must convert the fuel volume to mass in pounds. The method used to convert volume to mass was covered in a previous lesson on fuel. You can refer to CAP 696, section 1, page 4, paragraphs 5.1 and 5.2 for conversion data. We can continue with the next step. Enter the ramp fuel and multiply it by the arm to obtain the total ramp moment. The next step is to sum the mass column and the moment column to obtain subtotal ramp mass and moment. We can now calculate the subtotal takeoff mass by subtracting the fuel used for start, taxi and run-up, which is a fixed amount as explained in the note below the table in figure 2.4. To complete the table, the trip fuel, arm and resultant moment are entered, and then, subtracting their mass and moment from the takeoff mass and moment, we obtain the subtotal landing mass and moment. We have now completed the load sheet table and obtained the takeoff mass and moment and the landing mass and moment. We are now going to find the takeoff and landing centre of gravity by plotting our load sheet data onto the centre of gravity envelope in CAP 696, figure 2.5. This is a graphical representation of the mass and centre of gravity limits. The right-hand vertical axis is the mass in pounds and the horizontal axis is the centre of gravity position in inches aft of the datum. The diagonal lines represent the moment divided by a constant of 100. To find the takeoff centre of gravity, draw a horizontal line representing the takeoff mass from our load sheet of 3,642 pounds, and then draw a diagonal line indicating the takeoff moment, in this case 3,102. Where the two lines cross, drop a line parallel to the grid line to the horizontal axis, which will indicate the centre of gravity for takeoff, being 85.2 inches aft of datum in our example. Notice that this reading is acceptable because it is within the white part of the envelope and not in the shaded area which represents out of limits. The next step is to plot the landing mass by drawing a horizontal line representing this. Here it is 3,402 pounds, followed by a diagonal line with the moment. Here 2,922, and where the two lines cross, drop a line parallel to the grid line to the horizontal axis, which will indicate the centre of gravity for landing. Our result is 85.9 inches aft of datum, which is in the envelope and in limits. We have now completed the exercise using the loading manifest and centre of gravity envelope to obtain the centre of gravity positions for takeoff and landing, and importantly, shown that the mass and centre of gravity are in limits. We know from our previous lesson on definitions, the centre of gravity can be calculated by dividing the total moment by the total mass, which we could do for this exercise, resulting in the same answers for centre of gravity. However, the calculated mass and centre of gravity still have to be checked against limits. In comparison, you can appreciate that by using the graphical method to plot calculated values, there is an immediate check of being within limits.